So you guys all have a copy of the review packet. One small problem with it is I missed a page when I ordered the copies. So I have an additional page for you to add on to the end of that when I get it run. You notice in the last page is 16 out of 18. So I'll have that. I should have that for you next time. Will somebody try to make sure to remind me to hand those out? I'll do my best to remember, but it's always nice to have some backup. So the review packets due on or before the last day of class. So the last day of class is that X day. It's like the 22nd, I think. So it's about 2 weeks out. You'll want to do a good job on this review packet. If you complete it and turn it in, it's worth 5 points of extra credit onto your exam, plus you get to use the review on your exam. The exam format will basically be the same as the review packet, less questions, some different numbers or whatever, but it's like the same general idea. So you'll want to go slow through it, be thorough, take your time, make sure that like you're including information that you can use when you look at it later for like how to do the problem, not just like here's the answer. The idea here with the review packet is I want to take this exam and turn it from a memorization exam into a preparation exam. That if you do a good job on your packet and you answer your questions thoroughly and include like all the things that you need to remember on like how to do the problem, when it comes time for the test, should be a piece of cake. Additionally, I would say that you may even encounter some problems that are duplicate from the review to the test or to the exam. So again, you'll want to make sure you're doing a good job and trying to be thorough and double checking things and all that jazz, because you may find some duplicate questions where all you really need to do is just kind of like copy down what you wrote. Any questions about that piece? Okay. So last class we did our last test for the semester, so we'll just have the chapter 15 test to be the last test before the final exam. The tests have been graded and entered. I also put in the doubled high test score. If you do not want that and you want to do the retake instead, sometime over the next couple of days, probably by middle of next week at the very latest, I need an email from you saying that like, hey, I'd rather retake this test on this day, you know, in this circumstance, whether testing room or study hall or whatever. But I need that email pretty quick because we'd have, I think I counted like 5 class days, including counting the X day, left that we're going to meet. So that's not a lot of time left to kind of squeeze that in if that's what we're electing to do. We are going to cover one more set of topics before the end of the year. We're going to look at 2 sections. So we'll have like a day of, well, I'll talk about it and introduce the idea and assign a little bit of homework, and we'll have a Delta Math day and then another lesson, a little bit of homework, and another Delta Math day. And those will be our last 4 classes. So these final homework assignments will be the last grades in the grade book for you guys. There won't be a test for this last set of topics. You'll see them on the final, but there will be no test. There'll be no homework quiz for these last set of topics. Just going to be homework assignments and Delta Maths and stuff. So that's kind of gets us to the end of the year. Does that sound okay with everybody? Good. The other thing I wanted to say, when grading these last set of tests, it we use some interesting methods that I know that I didn't teach you, which I found quite suspicious, that there was some cell phone AIing going on during the test. For the final exam, you're going to turn in a cell phone for me to give you a copy of the exam. Nobody gets an exam until they've turned in their cell phone. The same would be true in any class you have with me going forward. We're just going to turn in a cell phone to get your test, and remove that as a temptation for you guys. So even further reason to like take some time on your review, do a good job. Like that's going to take the place of anything that you have helping you out. That's the help you get, which I think is still pretty excellently generous to get a review that you can use on the final. Especially one that's like this detailed and this, thorough. Everybody cool? All right. So today we're going to talk about sequences over the next 2 lessons. We're going to talk about first sequences and then series. These are 2 kind of like closely related topics. So one builds right on top of the other. And you'll even see when we talk about sequences today, there's a lot of ideas that are going to be just rehashing things that we've already done. So it's a really nice topic to kind of end the year with as it goes back and circles back to a lot of ideas that we've seen previously. So when we talk about a sequence is simply just a function, but it's a special kind of function. It's a function whose inputs are the counting numbers, like 1, 2, 3, 4, and the output can be any real number. So the numbers you can plug into a sequence, you can plug 1 in, you can plug 57 in. You can't plug a half in. It's not a whole number. You can't plug -4 in, no negatives. Can't plug 0 in. Positive whole numbers only are the only things that have outputs. Is everybody okay with that? So that's like the domain of every sequence is going to be those counting numbers or some subset of them. So some examples of a sequence. So one way we could write that sequence is just as like a list of numbers, like 5, 10, 15, 20, 25. That's a sequence. You could write as 2, 4, 8, 16, 32, ... 2 to the k. That's like telling us the general form, and then another ... The ellipsis is just kind of saying that we continue on for that same pattern. You could write it with as a set notation. So number 3, this is the set of things 1 over k, where the k's are the numbers 1, 2, 3, 4, etc. So the things in this set would be like 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. Or just kind of generically, you can call them a sub 1, a sub 2, a sub 3, yada, yada, yada. Is everybody okay with like one way to present a sequence? So when we talk about a sequence, the inputs for the sequence we call the term numbers, and the outputs for the sequence we call like the term value. So if I look at this first sequence, if I look at 10, 10 is the second term. So I might say that if I refer to this sequence as b sub n, I refer to 10 as b sub 2. So this is like your term number, and that's like the term value or the term of the sequence. So this should look a lot like, like a function notation, or reminds you a lot of like a function notation, where like we write f of 2 is equal to 10, where we plug 2 in and 10 comes out. We do the kind of the same notation for a sequence, but we use a subscript instead of that function notation. Is everybody okay with the way we're, the vocabulary here and kind of the what we're describing? So when we talk about sequences, we want to create a vocabulary of the way to describe the things that 2 sequences might have in common or might be different. So the first thing that we'd want to do is talk about the difference between the number of terms in a sequence. So we classify a sequence two different ways. We say that either a sequence has a finite number of terms, like example 1, where there's exactly 5 terms, 5, 10, 15, 20, 25. That's it. That's a finite sequence because there's exactly, in this case, 5 terms. Or you can have an infinite sequence, like example 2. I know example 2 is an infinite sequence because it has the ... at the end. So that's the sequence 2, 4, 8, 16, 32, and so on forever. That's an infinite sequence. It has an infinite number of terms. Is everybody okay with that? Now, when we come to describing a sequence, like a list of terms is fine, but it's not very informative. What we eventually want to do is be able to create a formula for describing the sequence. There's 2 different ways that we might write that formula. There's an explicit formula and a recursive formula. The explicit formula is based on the term number. So, for example, if I were talking about that first sequence, I might say the explicit formula is 5 times n, because when I plug 1 in for n, I get 5. When I plug 2 in for n, I get 10. When I plug 3 in for n, I get 15, and so on. It's based on the term number. So if I wanted the 100th term out of this, I can just plug 100 in for n, and it pops right out. The other way to write this, or the other formula to write this, is as a recursive formula. So that's based on the previous term. So when we write b sub n minus 1, that's just like our notation for the previous term. So if I look at this, I notice that like 10 is just 5 plus 5. And then 15 is just 10 plus 5. And 20 is 15 plus 5. And 25 is 20 plus 5. I'm just taking the term before it and adding 5 to it each time. So that's like a way to write it recursively. They're both describing the same sequence, but it's just a different way of doing it. Anthony.
Could you like minus 2 plus 10?
You can have lots of different ways that you could have, like we'll talk about ways to write these recursive and explicit formulas a little later. Right now I'm just doing it for you as an example. I haven't talked about how I'm doing it at all. So it could be a complete mystery, and if that feels that way, that is okay. We will like systematize it here in a moment. So that's what you're asking, right? Yeah. So we'll systematically create a way to do that here in a moment and talk about the kinds of formulas that I'll be expecting you to write, like the sorts of situations, because they can be very complicated, but I won't ask you to do anything that's very complicated. So, little example here. Find the first 6 terms and the 100th term of the sequence a sub k, where a sub k is equal to k squared minus 1. So I notice that this is an explicit formula because it's in terms of the term number, which is k. So if I want to find the first term, I'm just plugging 1 in for k, and I get 0. If I want the second term, I'm going to plug 2 in for k. I get 3. If I want the third term, I'm plugging 3 in for k, and I get 8. If I want the fourth term, I'm plugging 4 in for k, and I get 15. If I want the fifth term, I'm plugging 5 in for k, and I get 24. If If I want the sixth term, I'm going to plug 6 in for k, and I get 35. And if I want the 100th term, I plug 100 in for k, and I get 9,999. What do you guys think? It's okay? Relatively easy, right? It's just like basically just doing like function notation stuff where I'm just plugging the number into the equation, right? What if we want to do a recursive example? So it says find the first 6 terms and the 100th term for the sequence defined recursively by the following. So we're told the first term is 3, so we have the first term. And to find the subsequent terms, I take the previous term, so that would be 1, the first term, plus 2, and the first term is 3, so 3 plus 2 is 5. The third term is going to be the second term plus 2. The second term was 5, so 5 plus 2 is 7. The fourth term, well, I'm going to take the third term and add 2 to that. The third term was 7. It's 9. To get the fifth term, we'll take the fourth term and add 2 to it. So 9 plus 2 is 11. And to get the sixth term, we'll take the fifth term and add 2 to that. So 11 plus 2 is 13. Now, it also asks for the 100th term. Oh, no. Is that going to be easy to get? Not really, because what are we going to have to do to get it? We're going to have to find all 99 terms before it, right? This is the problem with the recursive formula. Like, while it's very simple to compute individual terms if you start at the beginning, but finding the next term is a very easy proposition. Finding a specific term in the future, well, that can be quite time-consuming. Now, we can do this anecdotally if we look at this, because this specific sequence is just, what are the numbers coming out? Just the odd number starting at 3, right? So if I have the odd number starting at 1, what is the 100th odd number going to be? 201, right? So you have your first 50 is 1, 3, 5, 7 up to 101. And your second 50 will be like 101, 103, 105 up to 201, I think. That's me just thinking about it. So if we're starting at 3, it's just going to be to 203, right? We just cut 1 off the beginning and put 1 more on at the end. Now, this one we got lucky because it was just odd numbers, and it was relatively easy to think about it. In general, that would not be the case, though, right? All right. And that's the downfall with a recursive formula. All right. The next thing that we'll talk about is if we're talking about infinite sequences, one of the things that will be of primary concern to us is, does this sequence converge or diverge? So by that, we're asking, if I take the limit of that sequence as n goes to infinity, do I get a finite answer? If so, we say it converges. If I get an infinite answer, the limit just doesn't exist at all, we say it diverges. So that's the vocabulary. Let's look at some examples here. So if I'm taking the limit of this first sequence, I'm looking at the limit as n goes to infinity, and they were nice here and gave us that general form. So let's think about what that limit is going to go to. As n keeps getting bigger and bigger and bigger, what's happening to the value of 1 over n? It's getting smaller and smaller and smaller. What number is it approaching as we keep getting smaller and smaller and smaller? 0, right? Because it's not going to go to negative, Brody, because all the values are positive. You have positive 1 over a positive number, so it can't go negative. Does that make sense? So the smallest it can get is 0. So because that limit exists and it's finite, we say that that series is convergent, or it converges to 0. Either it'd be fine. Now, alternatively, if I look at 1 over n, that looks like a rational function to me. You guys remember we studied rational functions earlier this year. Remember, to find the end behavior of a rational function, we had to look at the degree of the numerator and compare it to the degree of the denominator. If I look at 1 over n, the degree of the numerator is 0, because there's no variable, and the degree of the denominator is 1, because it's n to the first. When the degree of the numerator is less than the degree of the denominator, we had a horizontal asymptote at y equals 0, hence the limit goes to 0. So if you have a rational function, you can use those rules for the end behavior of rational functions to do these limit questions, which might be helpful. All right, if I look at b, they were not as nice to us on this one and didn't give us the general form, so we're going to have to come up with that ourselves. Hi, Miss Yarrow.
Dr. Gulick, how are you?
Great. How are you doing?
I'm appreciative of our teachers.
Thanks.
And in appreciation of our teachers, we're feeding you all until you can't fit into your pants this week. That's the goal.
That's why I've been wearing pants without...
That's why you're wearing sweatpants.
Yeah, the stretchies.
We have treats.
Okay.
Lots of treats for you.
Well, let me
I'm
go...
being disruptive.
Let me go...
And who has their head down behind you, Anthony? Who am I yelling at?
That's Ashton Gust.
Ashton Gust. Math is not important to you? Math. Yeah. Oh, you shouldn't be sleeping in class. Right? Yeah. So put yourself in a position that you're not going to go to sleep in class. That would be good. And I have steak pop and cookie drop. It is. I know. So that's awesome. Steak pop? Veggie drops? Yes. We don't know.
Thank you.
You are welcome.
Hi, I'm back.
I'm trying. Get your fat out, get your straws.
I mean, there's lots of goodies. All right. All right. We need an explicit formula for b. So if I look at this, the way I would look at this is I'm going to look at each fraction separately. So if I look at the first fraction, 2 over 1, what do I notice is the relationship between the numerator and denominator? The numerator is just 1 more than the denominator, right? Does that pattern hold on the next term? And the third term? And the fourth term? Okay, so to me it looks like I could write this as n plus 1 over n. Everybody see kind of what I did there to think about that? Again, that's not something that I would expect you to do by yourself and from whole cloth, but these are the examples the textbook I stole this from we're using, so we're just going to go with them. All right, so if I look at this one, Again, looks like a rational function to me. What's the degree of the numerator? 1, because it's n to the first. And the denominator, the degree is 1 also. When the degree of the numerator is equal to the degree of the denominator, we have a horizontal asymptote of leading coefficient over leading coefficient. In this case, that would be 1 over 1. So again, we'd say this is convergent because that limit is finite. Let's look at the next one. Again, they did not give us that general term. All right, that's fine. But if I look at the numbers 2, 4, 6, 8, 10, what do we notice? They go up by 2s. What kind of numbers are they? They're all evens, right? How do I make an even number? Multiply something by 2. Right? You can't add 2 because if you start with an odd and you add 2, you get another odd back. So it'll be just 2n would be my explicit formula. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, etc. So if I think about this, 2n is just like a linear function, right? It basically just looks like that. What's its end behavior doing? It's going to positive infinity, right? So that limit is positive infinity. So we'd say this is divergent. You don't actually have to tell me what the limit is. You can just say divergent, and that's okay. And the last one, well, that's nice. They've given us the explicit formula. But this is kind of a weird sequence, right? What do you notice that's happening? It's going -1, +1, -1, +1, -1, +1. What's this going to be at when n goes to infinity? Can we tell? It's going to be -1 or +1. Which one, though? Can we tell? We cannot. This is one where the limit doesn't exist because it's impossible to tell whether it should be at 1 or -1. So all you Mean Girls fans, there you go. So again, the limit doesn't exist there because we can't tell whether it would go to -1 or +1. There's no way to tell because infinity isn't odd or even, and we notice that all the odd ones are -1, all the even terms are +1, but like infinity doesn't have a, isn't odd or even, so there's no way to tell. Does everybody feel okay there? We'll do some more examples of this in a moment. Again, I wrote in the rules for rational functions here. So we said them aloud while we were doing it, but I wrote them down here in case you wanted them in one place. All right. So, same kind of problem again. So we're looking at the limits of these sequences. If I look at that first one, what's the degree of the numerator? Degree of the denominator? So the limit should be not 1. It's going to be 3 over 1, or just 3. So we'd say that's convergent. Okay, what about the next one? What's that limit going to be? Can be what? It's not 1. What's the degree of the numerator? And the degree of the denominator? So the degree of the numerator is less than the degree of the denominator, which means the horizontal asymptote is at y equals 0. So the limit here is 0. But again, still convergent. How about this one? What's going to happen on this last one? The limit exists, but the sequence is divergent, so you're very close. The limit is infinity, but we don't need to write that. We can just write divergent once we see it's not convergent, right? So if you look at this, the degree of the numerator is 3, the degree of the denominator is 2. When the degree of the numerator is greater than the degree of the denominator, we had to do that polynomial division thing, right? As soon as you see that, it's divergent. You don't need to come up with what the limit actually is. It is infinity because you have a linear function when you do the division with a positive slope. But we're not asked to actually find that limit. We're just asked enough to say divergent. So like in this case 3, that's always divergent. And these first 2 are both convergent, right? Now, Mr. Kulik's been writing explicit formulas and recursive formulas for these sequences kind of all willy-nilly without giving you any instruction on how to do this yet, right? I've just been kind of doing it for you and like explaining what I saw, but there's a more systematic way to approach this, at least for certain kinds of sequences. So in this class, I will ask you to be able to write recursive and explicit formulas for 2 specific kinds of sequences. Those kinds of sequences are called arithmetic sequences and geometric sequences. So an arithmetic sequence, if I look at the consecutive terms, there's a constant common difference. That means that we're like adding by the same amount or subtracting by the same amount to go from one term to the next term to the next term. We call that constant common difference D. And so if I have that the first term is 1 or is A1, I can write the explicit formula by just doing the first term plus n minus 1 times D. That'll give me the equation or the formula for the explicit form. And similarly, to write the recursive form, I can just take the previous term plus D. So let's do an example. We're not going to do this example 2 because it's more complicated than I want to get into. So it says for the arithmetic sequence, find first the common difference, then the 10th term, then the recursive rule for the nth term, and then an explicit rule for the nth term. I'm actually going to do part B last because I'm going to use the explicit form to find the 10th term, so I can just plug the 10 in for n and be done with it. So if I look at this, it tells me it's an arithmetic sequence. So I'm just going to look for a number that I can add or subtract each time. So what do I have to add or subtract from -6 to go to -2? We add 4, right? And to go from -2 to +2, we add 4. And to go from +2 to +6, we add 4. And to go from +6 to +10, we add 4. So what that tells me then is that common difference is 4. So that's my answer for part A. We're going to do part C next. So the recursive formula is right here. So I just write the previous term plus the D, which is 4. But I also have to list the starting point, right? If it's based off the previous term, it needs to have a start. So I also need to write that the first term was 6. Is everybody okay there? Very easy formula to write, right? You're just basically plugging one number in and writing down the first term. For the explicit formula, I have to plug in the first term and the D. So if I do that, -6 was the first term, and D was 4. And if I distribute the 4 through and combine some like terms, that would be 4n minus 10. And now that I have that, doing part B where they ask for the 10th term is super duper easy. Where I can just plug the 10 in for n and I'm done. I don't have to generate any more extra terms. How do you guys feel? So what we want to think about here when we think about these arithmetic sequences is these guys are going to behave just like a linear function. Because if I look at my answer, 4n minus 10, it just looks like ax plus b, right? So that's when we think about arithmetic sequences, we think linear function. So everything that we could do with a linear function, we can do with an arithmetic sequence. It's basically the same thing. Everybody good? Okay. The other type of sequence we'll talk or expect you to be able to write an explicit or recursive formula for is a geometric sequence. Geometric sequence is typified because the consecutive terms have a constant common ratio. That means if I divide one term by the previous term, I'm going to get the same result every single time. We call that the constant common ratio, and we abbreviate that with the letter R. So our explicit formula is just the first term times that R to the n minus 1, or our explicit form is just the previous term times R. And again, I'm not going to do the second example for simplicity's sake. It's a little more complicated than I care to dig into right now. So if I look at this sequence of numbers, 3, 6, 12, 24, 48, we're told it's geometric. So I'm looking for what times 3 gives me 6. Well, that's 2. And then 2 times 6 gives me 12. And 2 times 12 gives me 24. And 24 times 2 gives me 48. So I can see right away that the R is 2. Just like in the previous example, I'm going to skip finding the 10th term until I have the explicit formula. So let's go to the recursive one next. Up above, that says that all I need to do is take the previous term and multiply it by r, and then I also have to give a starting place. So it's just going to be the previous term times 2, and the starting place was 3. So to write the explicit formula, I just do the first term times r to the n minus 1. So the first term was 3, the r was 2, and I'm done. No big deal, right? And now that I have that, I can find the 10th term. So 10 minus 1 is 9, 2 to the 9th is 512, and times 3 is 1536, I think. Anthony's going to check it for me. 3 times 2 to the 9th, is it 1536? She was here about 10 minutes ago with the snack cart. Guys feel so far so good? Fairly straightforward, right? This is not tremendously complicated. This last type of question can be the most difficult question, but we're going to take advantage of work that we've done previously and our graphing calculator to make this problem quite a bit simpler. So this says the second and fifth terms of a sequence are 3 and 24 respectively. Find the explicit and recursive formulas for the sequence if it's arithmetic or geometric. So it says the second and fifth terms of the sequence are 3 and 24. So it's telling me this. Everybody okay with that? And to write this, I need to do, here's my explicit formula. And then I need a recursive formula. So the idea, what I'm going to do here, is I'm actually going to think about these two terms as an XY table, where the X is going to be like my term number, and the Y is going to be like my term value. So I'd have the 0.23 and the 0.524. So far, so good? And because I know that this is linear, what I'm going to do is I'm going to fire up my calculator, and I'm going to enter this data into my calculator and ask my calculator to make a linear equation out of this data. So to enter the data into my calculator, I press the Stat button. I go to the Edit tab, and I type the X's into like L1 and the Y's into, say, L2. So give you a moment if you're following along to do that. Once I've entered 2.5 into L1 and then 3.24 into L2, I'm going to exit out to the main screen. I'll go back to the Stat menu, but this time go to the Calc tab and I'm going to select the linreg command. I'm going to make sure that my X list and Y list match where I just typed those points. Mine were in L1 and L2 respectively. And then hit or calculate. And so what popped out was A sub n equals 7n minus 11. Anthony. I always do the AX plus B, although it doesn't matter as long as you put the numbers in the right spot. Whether you call it negative 11 plus 7n or 7n minus 11, it doesn't really matter. So that's my explicit formula. Now my recursive, I need the first term and the D. So the first term is easy. All I got to do is plug 1 into my explicit formula. Piece of cake. And the slope is just going to be my D. So my recursive formula then, the previous term plus 7, when the first term is negative 4. Easy peasy, right? Now for part B, it asks us to do the same thing if it's geometric. So again, I need to write a explicit and recursive formula. I'm going to do this the exact same way. I'm going to use the exact same data table, but if I look at my geometric sequence, what type of function does this look like? It looks just like an exponential function to me, right? Because the variable is in the exponent. So I'm going to do this the exact same way, but I'm going to do it exp reg. So I'll go back to stat, over to the calc menu, and scroll down to command 0, which says exp reg, short for exponential. My x's are still in L1, my y's are still in L2, so I'll just hit calculate. So this tells me then that my explicit formula is a sub n equals 0.75 times 2 to the n. Anthony, what's up? You okay?
Yeah.
Okay. So that's that. That's my explicit formula. Done. Now for my recursive, I need the first term and I need the R. Well, the R is easy. That's just 2 is my R. And to get the first term, well, I just need to plug in 1 into my explicit formula. And there's everything I need, right? How do you guys feel? Calculator makes that a breeze, right? If you had to do that by hand, what you would do is you'd like plug this in for you'd take the first point, plug that in for a sub n, and that one for n. and then use the second one, plug in for A sub n, and then plug in for n. And then you'd have a system of two equations to solve, which, again, not terrible, but like, if I don't have to do that, I just assume pass, right? Nobody wants to solve a system when the calculator can just handle it for them. So that method, calculator method I've shown you, is acceptable to use on a quiz or a test, for me anyways. So your assignment, we're just going to be using these homework problems that I've posted in. Let's do 1 through 31 odds. That's like 15 problems or something. And then I'll have a delta math based on this same set of topics for you guys next time. Class after that, we'll do the series stuff, get a little homework assignment based on that, and then do a delta math based on the series stuff. That'll probably be the last next day of class. So we won't have like full-fledged time in class to work on the review. That's why I'm giving it to you like 2 weeks before it's due. So don't forget about it. Don't leave it for the last minute. Work on it a little bit when you're fresh. Go till you start getting tired, because you don't want it to get sloppy. You don't want to do a bad job on it. You know, like, try to do a couple pages, a page or two a day, and you should have no problem getting the thing done in, inside of 2 weeks. Some of the stuff will go quick that you remember. Some of it might go slow because it's like, ooh, I have to really remember how to do this. But feel free to write yourself like little notes of how to start, or what things mean, or if there's a formula that you need to use to do something. All of that can be included. I tried to leave a fair amount of space on the sheet, that if you're being neat about things, you should have plenty of space to include in directions to yourself and all that kind of jazz if you need it. But that's it for me. How do you guys feel okay with today? This shouldn't be too bad at this point in the year. We've done, like, all the complicated ideas are things that we've done before. It's just like getting used to a little bit of notation, which again is not so different than just like a function notation. So there you go.